Hi, this is Qian Wang from Shanghai Jiao Tong University. And this video was remade after the webinar was completed because we have encountered some technical issue. And my talk is about the classification for COVID-19 from community-acquired pneumonia, or CAP. And this work is jointly done with United Imaging. And in 2017, our university has cooperated with United Imaging, and we have founded the Institute for Medical Imaging Technology. Since then, we have pushed up for some active cooperation of researchers. And this work is actually a product of such cooperation. And during past months of some difficult time, and as part of a rapid response, we have part of our team, our students, collaborators, and we have worked really hard to make progresses in this direction. Okay, so let's come to talk about COVID-19. And we all know that it is critical to identify, to track, and to quarantine patients to fight against the pandemic of COVID-19. And currently, PCR is used as the gold standard for making a final diagnosis. But if we rely on PCR only, and then there might be several issues. Among them, we have seen the shortage of testing capacity. If we are unable to deliver testing service in a sufficient number, and very likely we will have to leave many patients untested. Since the viral transmission of the coronavirus is really rapid, in this way, we have witnessed cluster outbreaks that have been occurring in many different countries again and again. And another issue points to the false negative ratio. So a patient might have developed some symptoms already. Then the PCR test would possibly just return a negative result. And we have to retest the patient for multiple times and finally get a positive reading. At the same time, chest CT, it is relatively easy to deploy, and it is fast for diagnosis. And very importantly, the price or the economic cost of chest CT is kept at a relatively comparable level to PCR, at least in China. And that is a very important reason that chest CT is recommended as a major tool for clinical diagnosis and assessment of COVID-19. We know that there are many typical image features for COVID-19. For example, we have seen GGO, or ground glass opacity, and sometimes it is reflected as consolidation in the lungs. The problem is that it is still very challenging to do a differential diagnosis of COVID-19 with respect to many other different types of infectious pneumonia. There's little CT characteristic that is specific for COVID-19. And many signs actually overlapping with each other for different types of pneumonia. So in this study, we set our goal as to classify COVID-19 and this community-acquired pneumonia, or CAP, based on 3D CT images. And to perform this work, we have prepared a really large multi-center collection. And we have cooperated with 8 hospitals that are in 7 cities that are located thousands of kilometers away from each other. In total, we have recruited about 3,645 patients, and we have scanned nearly 5,000 CT scans from them. And we, by the way, all these images are thin slice reconstructed, and the thickness is ranging from 0.625 to 1.5 millimeter. And we split this data into 2 sets. The first set is has about 1,588 patients with nearly 2,200 CT images. And we use this set for training validation. And we will do 5-fold cross-validation on them. The second set has about 2,857 patients with nearly 2,800 CT scans. And this splitting of these 2 sets is done at the hospital level. That means that if we train some model from the first training validation set, and then we apply this model to the second one, this kind of testing can be regarded as a completely independent one. So for classification, we have adopted a 3D ResNet as a backbone. And in pre-processing, we mask all images with the masks of lungs. That means that we only focus on the lung areas, and we want to exclude the influence from these nearby background areas. And our images are center aligned, and we resample them to the size of 256 by 256 by 138. We have also applied an HU window for proper intensity normalization of all images. And the loss function in training for the network is set to the binary cross entropy. And in training, we have, and training is done with 4 Titan RTX GPUs. And with a network, one may compute the so-called class activation map to check the responding feature maps that are varying across individual spatial locations. We just go one step further to use convolutional layers to calculate the class activation map. And we further use the mask of a pneumonia infection to help the network for refining the attention. So basically, we derive the attention map from the network, and then we compare the mismatch between the attention map and the ground truth of the segmented infection mask. So the point here is that we want to make sure the attention is located within the mask only. That means that the decision of the network is done by using visual information extracted from these infections instead of other areas. So by increasing the adoption of visual cues of these infections and getting aware of how these anatomic structures are actually going on, we have achieved a better interpretability for our trained model. And it is critical to precisely label lungs and infections in our implementation. And very fortunately, we have access to this in-house tool of VBNet. So basically, VBNet is developed from VNet, and it's specially designed or adapted for the handling COVID-19 CT images. So we have shown some typical segmentation results for 2 COVID-19 patients, and the lung is labeled, and within the lungs we have seen some blue masks. So basically, these blue labels are for the infection areas. And for the infections, the dice ratio is reported to be as high as nearly 92%. So we just check closely of how images are appearing in our data set. And we conclude that this COVID-19 case usually shows more severe infection than CAP. We just use the VBNet segment all images in our data set, and then we can quantify the severity by computing the volume ratio between the segmented infections and the lungs. And then we, on the right, we show a distribution, and the horizontal axis of this distribution is the ratio, the volume ratio between infection and the lung. And we can see that most these CAP patients, they tend to have small ratios, which are indicated by these blue bars. And for COVID-19 patients, the severity is much higher, which is for these red bars. So we have seen that these red bars are mostly in the right half of this figure, but these blue bars are distributed, concentrated in the left half. So imagine that we have such a data distribution, then it is very likely the trained classification network would be dominated by the volume ratio, because the network can simply treat this ratio as a major feature when making the decision. But that's not the truth. Basically, even someone has COVID-19 and some very large infection, this kind of infection is growing from very tiny to big to bigger. So a successful network would have to identify this COVID-19 patient, even though this volume ratio is very small in the very beginning. So to solve this problem, we have proposed a so-called size-balanced sampling strategy to address it. So basically, as in the usual way of deep learning, we can apply this kind of a uniform sampling to treat all images or training images equally. And with our attention model enabled and the backbone of ResNet, we have trained some network, which is showing on top half of this figure. And on the bottom half, we have introduced this size balance sampling and train a second network. So we just set a threshold on the volume ratio between infection and lung. So basically with this threshold, we can cut all these COVID-19 patients into two parts, into two groups. The first group is for COVID-19 patients with small infection, and the second group is for these patients with large infection. And similarly for CAP patients, we can do the same thing, and we have two groups. So in total, we have 4 groups of images for training. And then if we do uniform sampling to them, all of these 4 groups, they have different sizes, have different numbers of different numbers of training subjects inside. So if we do uniform sampling, then in every minute batch, we will have different numbers of subjects that are contributed by these 4 groups. So in the size balance sampling, we just manually control the sampling rate or the probability to draw a certain subject from one of these 4 groups. And we make sure that these 4 groups, they contribute equal numbers of training subjects, training images in the so-called size balance sampling. And with this strategy, we have trained a second network, which is shown in the red box. And with these 2 networks, we apply a very simple ensemble learning to fuse the predictions from these 2 networks and get the final diagnosis result. Here comes the experimental result. So some details can be checked in our paper, and here are just a summary of how these things are going on. And one may notice that we have done a 5-fold cross-validation for a training validation set. And since we have somehow we can derive 5 models here, we can apply these 5 models one by one to a test set. So we are able to evaluate the standard variation for these 5 different tests. And the issue is that the margin between the performance on training validation and on the test set is quite close with each other. It just proves that we almost avoid being trapped by overfitting. And also the standard variation by applying these 5 different models in cross-validation to the test set is quite small. It means that our network, our training is very stable to deliver the results and to be migrated to the test set. And we also have checked the results when attention module is enabled or disabled. And we have found that on a test set, when this attention module is enabled, the performance has been improved, and this improvement is significant because we have some evaluation to the p-value, and this p-value is pretty small. And we just go one step further to check how these results are actually going on in the test set. And we have introduced the dual sampling strategy by combining uniform sampling and the proposed size balance sampling. So in size balance sampling, we have arbitrarily broken the law of the conventional way of sampling data, of sampling images, and usually it's easier for us to be trapped in overfitting by adopting this dual sampling strategy. However, these results show that with this dual sampling strategy, you can still largely preserve the classification capability when compared with using uniform sampling only. And more importantly, we have somehow improved the performance for these COVID-19 patients with small infection. That means that they are the minority in the COVID-19 groups. And at the same time, the performance also improves for CAP patients with large infection, also a minority group in the data sets. So here are some attention maps. So typically, we can use these attention maps to check whether this decision making is really making sense. So we can see that with the ResNet backbone and this conventional uniform sampling, somehow for most cases, this attention is located within lungs. And with our attention module enabled, we can see that this attention is much refined. It can most of these attentions are distributed in a very overlapping way with respect to the segmented pneumonia. But there are also some failure cases. For example, here we can see that if we only use the original copy of ResNet plus uniform sampling, and then this attention map does not always make sense. And for those cases, somehow our model can improve the attention localization by a lot. But still, you can see some attention has been linked to the outside area, for example, in the background. So it means that we still have many issues to resolve, and we are doing we are still working on this direction. And here's some conclusion. We have proposed a 3D CNN network with online attention refinement or refocusing and dual sampling strategy. And we apply this model to COVID-19 and CAP classification from CT images. And to verify the proposed network, we have conducted possibly one of the largest multi-center evaluation in the world. And we have achieved relatively high scores with an AUC equal to 0.944 and accuracy of 0.875. So this is our work, and thank you very much for watching this video and for participating into our event. And if you want to see more details about our work, please visit our paper is available at the archive and will shortly be published in IEEE Transactions on Medical Imaging. Thank you very much.